Hello and welcome back to a new video in which we'll talk about dynamic concepts. This is some work we did with Reda Al-Hinai, who is a lecturer in the University of Technologies and Applied Science in Oman, and also with the University of Sydney. So some of the models that we will see here belong to them. So what are dynamic concepts? A dynamic concept is an idea that allows you to observe from a high-level perspective the behavior of a system or the output of a system based on the inputs or a disruption in the inputs. And these dynamic concepts are very particular to simulation models. And there are a variety of them. And they allow you to tell a story on why things happen the way they happen. So I know this is a bit abstract, so we will show you during this video series a bunch of examples. On this video, we will talk about one of the most important ones, which is emergence. So let's get started.
Emergence is when a structure is observed to have certain properties that its parts do not have on their own. So these properties or behaviors emerge only when the parts interact in a wider whole. So it is the phenomenon where complex patterns, behaviors, or properties arise from the interaction and collective behavior of simple components or entities within a system. Now, a common example of emergence in nature is the structure of mounds that are built by termites. So these mounds are structures that termites build above their nests. Now, these termite mounds appear to be constructed by intelligent cooperation. So these complicated channels and chimneys control the airflow to manage temperature and humidity inside the nest. But individual termites, in fact, have no notion of how to build a nest. In fact, they are very far from intelligent creatures. These individual termites cannot even perceive the overall shape of the mound, let alone direct its design. Instead, these termites respond to very local chemical cues left behind by other termites and as well to temperature and humidity and airflow cues that are affected by the shape of the nest, the wind currents, the amount of heat generated within the nest, and other local phenomena. So these local perceptions are the only thing that actually lead to this complicated structure at the higher level. Now, another example of emergence is the formation of symmetrical patterns in snowflakes. So these snowflakes crystallize in a fractal pattern because of the way the water molecules bond together as the snowflake forms. So the growth of these snowflakes is also affected by the temperature and the humidity of the air as it falls through the atmosphere. So the combination of all these factors result in the unique and complex shapes that we see in snowflakes. So as an application, we are going to see a simulation model and we are going to check out how we can easily detect emergence through this simulation model. So this model is related to the dynamics of sears. So it shows how any disease with certain characteristics can spread. So you can do some research regarding sears in order to learn more details about it. But just for you to be able to understand what's going on, there are four states for the agents, which are people in this case. They can be susceptible, exposed, infectious, or immune. So let's run the model. So as we can see here, the animations clearly show the formation of patterns at the high level. Now at the micro level, the entities are randomly distributed at the beginning of the model, and each of these entities have certain characteristics which are also randomly assigned. Now, these entities, as I already said, are people in this case, and they are susceptible to the virus infection. Now, although none of these entities exhibit any kind of movement, the overall system behavior, as we were able to see, convey the ripple effect. So these apparent movements show how the virus propagates in the population. These results cannot be explained or predicted from the entity's individual properties or behavioral interactions. And this is actually what distinguishes the phenomenon of emergence. Now, there are usually certain characteristics of the evolvement of the system that we can easily distinguish visually when we look at the animation. So, for example, in this case, one of the things that can help us deduce certain characteristics about the system is the width of the strips that we see, the color strips. In this case, for example, these strips appear to be narrow. So this means that the evolvement or the spread of the disease is not very fast, so it is moderate. Now, if we increase the number of people contacted by each person per day to 7 instead of 5, this means that probably the virus is going to spread faster. So let's run the model to see how we can see this in the animation. So as we can see, we can still see the same ripple effect. However, we can see that the strips now appear much wider and that we are going to reach a unified color much more quickly, which means that the virus is spreading more quickly as well.